Welcome back to the deep dive. Today, we are shortcutting your learning curve on one of the most critical questions in AI right now. And it's maybe one of the most philosophical, too. How do we understand the behavior of these machines that are, well, they're shaping our world? We're talking, of course, about large language models, LLMs.
The GPTs, the Geminis, the Claudes, all of them.
Right. And they've scaled so far beyond just generating text. They're now these powerful systems that can do complex reasoning, they can write functional code, they demonstrate what really looks, on the surface like genuine intelligence. And with that rise in influence comes huge utility, but also a much greater potential for unforeseen harm.
Especially if we can't reliably predict how they'll behave in new situations.
Exactly. So our mission today is for you, the learner, to gain a shortcut to understanding the how and the why behind LLM behavior. We're moving beyond simple performance scores.
Beyond the benchmarks.
Yes, beyond benchmarks and diving into a brand new cross-disciplinary field of inquiry, machine psychology.
What's so interesting here is how naturally this discipline has come about. Machine psychology, or MP, is really just applying behavioral experiments we've used for decades to understand humans and animals.
But on LLMs?
But on LLMs, the core idea is that we treat the model as a computational black box. So instead of trying to peer directly into the trillions of weights and activation patterns.
Which is almost impossible anyway.
Right. We just focus purely on the relationship between the input, what we give it, and the output, what we observe.
Okay, so let's unpack that black box idea because, traditionally AI explanation has had two other very well-trodden paths. Path one, we could call it the neuroscience approach, is mechanistic interpretability.
That's right. Mechanistic interpretability is the deep dive into the guts of the model.
Into the circuitry.
Exactly. It's trying to map specific internal components weights, activation patterns, to understand precisely how a behavior is implemented. It's all about finding the circuits.
And then path two is what everyone knows, traditional machine learning benchmarking, just giving the model a test.
A standardized exam, basically. You give it a fixed data set and you get a single score back.
So MP is this third way, this psychology approach. It's a middle ground.
A necessary middle ground. It uses experimental manipulation of the inputs to try and reveal underlying constructs.
Oh.
Things like, logic or causality or even theory of mind. MP isn't just interested in the 90% score. It wants to know how the model got that score. What strategy did it use? And does it stick to that strategy when we change the conditions?
So it's about consistency, not just performance.
Precisely. And this behavioral approach is so critical because, realistically, the sheer size of these models means their behavior is often too complex to predict just from what we currently understand about their internal wiring.
That sets the stage perfectly for why this behavioral approach is so important right now. It's a direct response to the limits of those older paradigms.
Especially now that the models are internet scale.
Right. The traditional benchmarks really struggle. I mean, when you train a model on the entire internet, how can you guarantee a clean train to split?
You can't. You might just be testing for memorization instead of real generalization.
And that's not even the biggest problem, is it?
No, the bigger problem is that these LLMs show these surprising, almost magical emergent abilities.
Things they were never programmed to do.
Exactly. Things that weren't explicitly engineered. Few-shot learning is the classic example. The ability to learn a new task from just a couple of examples in the prompt without updating its core weights. That just emerged from scale.
And you can't analyze that with traditional methods.
You can't. It resists that kind of component-based analysis.
So the goal has to shift. We're moving away from asking for a single IQ score and more towards demanding a diagnostic evaluation that really characterizes the model's behavior under stress.
Exactly. And that shift is critical for, I'd say, three big reasons. First, the LLM's behavior, the text output, is the only thing we as users actually interact with. So if you want safety, you have to understand behavior.
Makes sense.
Second, behavioral methods scale. It doesn't matter how big the model gets, you can still test its inputs and outputs. And third, and this is a really practical one for researchers, it's often the only option when you're dealing with closed-source proprietary models. You can't see inside, so you have to study behavior.
Okay, but if we're going to borrow from psychology, we have to borrow the disciplines. Well, it's historical baggage, too.
Right.
We have to talk about a huge methodological caveat, the danger of self-report measures.
Oh, that's a crucial point. We already know that things like personality tests are questionable for humans.
Right.
For an LLM, they become even more suspect. If you prompt a model to rate its own personality, the results are just wildly sensitive to how you phrase the prompt.
It's almost absurd. You can tell it to act like a libertarian or a socialist in the system prompt, and then it will self-report its morality based on that role play.
Exactly. It's not revealing an intrinsic trait. It's just outputting a likely sequence of text.
So no personality tests for AIs.
Not like that, no. It's why MP has to be hypothesis-driven and use very stringent controls, just like good empirical psychology. You have to constantly ask, does seeing behavior Y reliably mean construct X is present? Or is there a simpler explanation?
And there's also the classic performance competence distinction.
Right, the Chomsky idea from 1965, just adapted for machines.
Meaning if a model fails a test, it doesn't automatically mean it lacks the core ability.
Exactly. A person can make a simple math error under pressure, but that doesn't mean they lack the competence for math. That same inconsistency applies to LLMs. We need really careful experimental design to figure out if it's a real capability gap or just a failure to perform under, say, a weirdly phrased prompt.
That distinction naturally leads us to the toolkit itself. If those older methods are struggling, what specific behavioral science tools are researchers actually borrowing? Let's dive into the first one, which I think is very relatable. Heuristics and biases.
So the heuristics framework from Tversky and Kahneman is all about the mental shortcuts, the biases that humans use. And early on, researchers found that models like GPT-3 showed biases that were remarkably similar to people.
Things like anchoring and confirmation bias.
Yep. But here's where the story gets a twist.
Okay.
And it's a surprising fact from recent research. A lot of those very human-like cognitive biases that were so common in older models well, they've largely disappeared in the latest generation.
Really? So they're becoming more rational?
In a way, yes. The thinking is that modern alignment techniques like instruction tuning and RLHF have basically nudged the models towards logical consistency and away from human irrationality.
So they've been trained to avoid those common shortcuts.
Right. But they still suffer from one major pitfall that's very human, framing effects.
But it's just about the wording.
Absolutely. An LLM will reason more accurately about a familiar, believable scenario than an abstract one, even if the underlying logic is identical. The semantics still influence the cold calculation.
Okay, moving from individual thought to interaction. Let's look at social interactions. Here, the big test researchers are borrowing is theory of mind.
Tom, yeah. It's key. It's the ability to infer that someone else has unobservable mental states, like a false belief that's different from your own reality.
The classic test where one person moves an object and you have to guess where the second person thinks it is.
That's the one. And the results are fascinating. Early models were terrible at this, but later models show a remarkable and very rapid increase in the ability to reliably infer those mental states.
So it might be an emergent property that just appears at a certain scale?
That's the hypothesis.
Yeah.
And researchers are pushing the limits now, testing higher order, Tom, that's recursive reasoning, and even seeing if LLMs can induce false beliefs in other AI agents in games.
And they're not just studying them individually, they're studying them as social groups.
Exactly. Looking at how they cooperate or coordinate in games, or even how networks of AIs form and evolve over time, using principles straight out of sociology.
Okay, our third area is the psychology of language, or psycholinguistics. This feels like a natural fit.
It's a foundational area. One common technique is using surprisal measures. Basically, how statistically surprised the model is by the next word in a sentence. You can use that to study how it handles really complex syntax.
And one of the best examples of this is the garden path sentence. Can you explain why those are so useful?
A garden path sentence is one that tricks you. It leads you to an initial incorrect interpretation because of its ambiguous structure before the end of the sentence corrects you.
The old man, the boat.
Exactly. A human stumbles over that. And what the research shows is that larger instruction-tuned LLMs don't just stumble. Their internal state and their responses actually approximate human responses, including human error patterns. It suggests they're parsing structure in a way that behaviorally mirrors our own cognitive limits.
Finally, let's talk about learning, specifically the emergent ability that really defines this era, in context learning, or ICL.
ICL is everything right now. It's the model's ability to learn a new task or a new rule just from the examples you give it in the prompt. No weight updates needed.
And this ability is just exploding. We're seeing models learn entire synthetic languages from context alone. So what does machine psychology tell us about how ICL works?
Since it wasn't programmed in, we're using cognitive modeling to kind of reverse engineer the learning algorithm. Researchers compare the model's output to different theories of learning.
Like, is it learning an abstract rule or just memorizing the examples?
Exactly, rule-based versus exemplar-based generalization. And what we're finding is that the model does a bit of both. Understanding its inductive biases when it shifts from one strategy to the other is critical for predicting how it will behave on totally new data.
Okay, all of this incredible work brings us to a really practical question. How do we make sure these experiments are actually robust? How do we avoid repeating, say, psychology's reproducibility crisis?
This is so important. LLMs are notoriously sensitive to tiny changes, and computer science hasn't always been an empirical science that demanded this kind of control. The single biggest risk is training data contamination.
Right. If you just copy-paste a prompt from a 1980s psychology paper, the model might just be recognizing it from its training data.
It's just memorization, not reasoning. That's why recommendation 1 is that prompts must use new wording, new agents, new actions. Ideally, you use procedurally generated experiments where the content is created by an algorithm on the fly. That pretty much eliminates contamination.
And recommendation 2 is about the prompt's structure and controlling for the model's own biases.
Yes, we have to use batteries of varied prompts, not just a few convenient ones. We have to control for things like recency bias, where the model pays more attention to information at the end of the prompt.
So if you have a multiple choice question, you have to shuffle the answer order.
You absolutely have to. And you have to watch out for things like majority label bias in few-shot settings, where the model just starts defaulting to whatever answer was most common in your examples.
So once we've designed this clean, contamination-free prompt, how do we get the model's absolute best performance out of it? The most famous technique, which has just revolutionized LLM reasoning, is chain of thought prompting.
Yeah.
And it's often as simple as adding the phrase, let's think step by step.
It's fascinating because it forces the model to externalize its reasoning. By asking it to decompose the problem, its performance can improve by 20 or 30%. It's like giving it permission to think before it answers. And we see other techniques like least to most prompting or even self-reflection, where the LLM recursively improves its own output. And the key is, these techniques aren't just tools. They become objects of study themselves, telling us how the model changes its strategy.
And finally, we have to manage the basic parameters, the randomness and the scale.
Right. You have to test across different model sizes, because sometimes we see inverse scaling, where bigger models actually do worse on certain tasks.
Bizarre.
And you have to control for randomness. Use a temperature setting of 0 if you need a deterministic answer. If not, you should be reporting averages across multiple runs to characterize the model's true potential, not just a single lucky guess.
Oh.
So what does all this mean for AI explainability as a whole? It really brings us to this debate over thick versus thin descriptions.
That sounds like a philosophy class. What's the difference?
A thin description explains AI purely through its internal parts, an activation map, a specific circuit. It's reductionist.
Okay.
Machine psychology argues for thick descriptions. This means using psychological terms, reasoning, intuition, personality, to add a layer of explainability when the inner workings are just too complex for a human to understand.
It's like how we explain human behavior. We don't need to detail every synaptic firing to say someone is a good planner. We use the higher level concept.
Exactly. Thick descriptions give us explanatory power to make sense of black box behavior when the thin, mechanistic descriptions just aren't enough, which is happening more and more with these giant systems.
Ultimately, this new discipline is a crucial addition to our toolkit for both AI explainability and AI safety research. It helps us predict the future behavior of these powerful, opaque, and increasingly complex AIs. So, here's a final provocative thought for you to mull over. Imagine if researchers started to apply the exact same psychology tasks repeatedly to LLMs over time. This would yield longitudinal data tracking the cognitive development of the same entity over months or even years. It could establish baselines that let us actually track the development of reasoning in AI. So the question is, what fundamental knowledge would we gain about machine cognitive development that we have never been able to obtain about the complex, messy, and fundamentally unrepeatable process of human development?